Hi, everyone. Before we start with the empirical rule, let's remember that Chebyshev's theorem said that at least 89% of the data values had to lie within 2 standard deviations of the mean, and that at least 89% of the data values had to lie within 3 standard deviations of the mean. In fact, all 100% of the data values could lie within 2 or 3 standard deviations of the mean. The 75% and the 89% were lower bounds. They weren't estimates. They were lower bounds. It could have been 100%. But now, for more precise results, we can go to the 68, 95, 99.7% empirical rule. Empirical means something that we see from observation. And in practice, we often see these bell-shaped distributions. Normal distributions are the most famous type of bell-shaped distributions. We'll talk a lot about those in this class. But when you look at this empirical rule here, notice that we have precise percents, but there's a price that we pay. We get more precise results, but we need an important assumption or condition, namely the assumption that we have an approximately bell-shaped distribution. If you have a distribution shape like that, or like that, or like that, then you cannot apply this rule. So we do get more precise results here, but we have a key condition that not all distributions satisfy. This rule is not robust. It's not distribution-free. But if we do have an approximately normal distribution, something like a bell shape like this, then what the empirical rule says is that about 68% of the data values will lie within 1 standard deviation of the mean. Chebyshev's theorem didn't say anything about data values within 1 standard deviation of the mean. The empirical rule does. The empirical rule also says that about 95% of the data values will lie within 2 standard deviations of the mean, and about 99.7% of the data values will lie within 3 standard deviations of the mean. Now, these are consistent with what Chebyshev's theorem said, because what Chebyshev said was that at least 75% of the data values would be within 2 standard deviations. The empirical rule says for this kind of bell shape, about 95% will lie within 2 standard deviations. And Chebyshev said that over here, at least 89% of the data values would lie within 3 standard deviations of the mean. The empirical rule says more precisely about 99.7%, basically everything, if you have an approximately bell shape. Now, what's a way of visualizing standard deviations when we have something that's about normally distributed, where we have about a bell shape like this? So those of you who have studied calculus may remember the idea of inflection points. These are points on the curve where the curve changes from concave up to concave down, or vice versa. So this would be a piece of curve that was concave up. Here's a piece of curve that's concave down. It's like curving up versus curving down. So over here, on this bell shape, the graph is concave up, CU over here. It's concave down in the middle here, and it goes back to concave up over on the right tail. The inflection points are the points here where the graph changes concavity. We also assume continuity, but that's a given. So the inflection points, the IPs, are where the curve changes concavity. Again, if you've taken calculus, these ideas may be familiar to you. If you haven't, don't worry about it. You don't need to know about inflection points in this class. But it is helpful if you want to get some sort of geometric sense as to what 1 standard deviation is, if you have a roughly normal distribution. So, what is 1 standard deviation? Again, think of this flag here at the mean, this flagpole at the mean. The mean line is the vertical line through the maximum point of this bell curve. Now, if we draw vertical lines through the 2 inflection points over here and over here, then 1 standard deviation, 1 sigma, will be the horizontal distance between the mean line and either inflection point. That's by symmetry. If you have one standard deviation from the mean line to this inflection point to the right, then you have one standard deviation, 1 sigma, between the mean line and this inflection point to the left. Okay, so one standard deviation visually is the horizontal distance between the mean line and either inflection point. You don't have to know that, but it's nice to know if you want to draw pictures that are accurate with bell curves, normal curves. So once again, the empirical rule says that with approximately normal data, about 68% will lie within one standard deviation of the mean, about 95% will lie within 2 standard deviations of the mean, and about 99.7%, almost all the data, will lie within 3 standard deviations of the mean. Now, these are not lower bounds. These are estimates. These are actual approximations. So if you have about normal data, then about 68% will lie within 1 standard deviation. It should not be the case that all the data, 100%, should lie within it. Chebyshev might say something like that, but no, the empirical rule gives approximate percents if you have about normal shaped data. And again, it's sometimes called the empirical rule. The 68, 95, 99.7% rule is sometimes called the empirical rule because approximately normal distributions are often seen in practice. And empirical means something that we see from observation. Next up, let's look at an example.